G'day, it's me again. In the last video I was rambling on a bit about these old 6.5 digit Hewlett-Packard meters, and particularly with using them to measure very low ohms, such as this 0.01 ohm or 10 milliohms resistor that I'd made up, or even things like these large current shunts and that. And the problem with using these meters directly to measure low ohms, even using 4-wire Kelvin clips, is that the test current that it passes through the resistance is only 1 milliamp. So the voltage developed across the resistor is very low. 1 milliamp times 0.01 ohms is 10 microvolts. So it's getting down into the noise. So it's hard to get consistent and therefore reliable accurate measurements. And the obvious answer to fixing that is to just use a much higher test current, which is what I did with this 16.5 volt battery. And I made up a 20 ohm resistor for the purpose, and this both limits the current from the battery to not hundreds of amps, but to only less than 1 amp, about 800 milliamps. And it also gives me something to measure the voltage across, so I know what the current is. And being about 20 ohms, it's up in the range where these meters can measure it accurately, and I get 19.985 ohms for that. So I know that accurately. From the voltage across it, I know the current accurately, and then measuring the voltage across here with a high known current, I can get a reliable, accurate measurement of the resistance of this thing. Now the trouble with that arrangement was that at 800 milliamps, these resistors were dissipating about 13 watts. That made about 0.4 of a watt across each resistor. And they're only rated at 0.6 watts, so they're running at about 2/3 of their rating, which makes them run pretty hot. And also then you introduce issues of temperature coefficient changing the resistance as they get hot. So the answer to that is come up with a different current source. And that's what I did. I just made this simple, just a heatsink with an LM317 adjustable voltage regulator with a resistor on its output connected to its adjustment input. So you put the volts in here on the inside of the regulator, the out through the resistors together with the adjustment, and you connect a load there to the negative side of the supply, and you'll get a constant current depending on what these resistors are. I've got 4 of them not only to get the right resistance but also to spread the load, because they're carrying the full current. So you don't want to dissipate too much power in any one resistor. Now these are 15 ohm resistors, so 4 of them in parallel gives us 3.75 ohms, and the current you get from that is the internal voltage reference voltage inside the LM317, which is 1.25 volts, divided by that 3.75 ohms gives 330 milliamps current. So that's what we should get. So if I put the battery in series with this, in series with this resistance, in series with this resistance, and then measure the voltage across that, I can verify that this is producing its 330 milliamps. And that should be much less than the 800 that was going through here. It should reduce the power dissipation by a lot, because power dissipation is I squared R. So if you halve the current, you quarter the power, and I'm more than halving the current, so I'm more than quartering the power, and these should not get hot as a result. So I'll put all that together and we'll measure something. So here's the whole mess. The positive from the battery goes to the positive of the regulator. The output goes through this 20 ohm resistor, and from that through my 0.1 ohm resistor and back to the battery. And we're measuring with the top meter the voltage across the 20 ohms, and the bottom meter is measuring the voltage across the 0.1 ohm. So applying power from the battery. The voltage across there is 6.622 volts divided by 19.985 gives us 331.4 milliamps. So very close to the 333 that we predicted theoretically from this. really that's all we need this for, because this is a constant current source, it doesn't matter if this is here or not. As long as the load off that is 45 ohms or less, because we've got 16.5 volts there, take away 1.5 for the regulator to use, so we've got about 15 volts available, and divide that by a third of an amp, and we get about 45 ohms. So as long as the load is 45 ohms or less, we'll be able to develop the full current, and it will give us a constant current for all resistances below 45 ohms. And this is what we've got there. There's battery going into the regulator through the 4 resistors, which at 330 milliamps, each one of these resistors is generating about 0.1 of a watt heat, and they're half-watt resistors, so they're okay. They're running at 1/5 of their rating. The adjustment connects to the other side of those resistors, and then that goes through our 20 ohm resistor where we're measuring the voltage across to verify the current. We get 6.624 divided by this resistance, which I've measured accurately, and it's that gives us 331.4 milliamps. That goes through our resistor under test where we're measuring the voltage, so the resistance is equal to whatever voltage we measure divided by that 330, that should be 0.3314, that should be. If we calculate that, that comes out to about 0.0116 or 11.6 milliohms. In the previous video I decided it was 11.7, but I think 11.6 is more accurate. So there we have it. This is really only, and it's getting very slightly warm. It's well inside its ratings now because we reduced the current from 800 milliamps down to only 330. So we really only needed this resistor to verify that the current is what we expected. So we can actually, if you look at the voltage there on that meter, the voltage across this guy, if I just take this resistor out of the circuit, so that was 0.3857, 0.3857 again, so we don't even need this anymore. Of course we don't need that. Disconnect, turn him off. Go one step further with these Hewlett-Packard meters. They've got a math function, and they've got several math functions, but one of them is a scale function. And there's 2 registers called Z and Y. And it adds the value of the Z register to the measurement and then divides by the Y register and shows the result. And if we recall Z, it's 0, and if we recall Y, it's 1. So it adds 0 and divides by 1, which is nothing. We just get the reading. So if I go implement that function, right, we get exactly the same reading. It's adding 0 and then dividing by 1. But what we can do, we can say stick 0.3314, which is the current running through the circuit, store that into the Y register. So now when we implement the scaling function, it'll add 0, which doesn't matter, but divide by the current, 3.3314. So it will be directly displaying ohms on the display. So I'll put maths, that function, and there we go. 11.6 by 10 to the minus 3, 11.6 milliohms. With just this and a power supply. And the math function, of course, but with other meters, if they don't have the math function, you have to do a little bit of arithmetic at the end. And if we take, say, this shunt, which is 100 amps, 100 millivolts, so that should be 1 milliohm. So I'll just stick the current, I don't need this second clip lead anymore, just stick the current into there and put the meter across the sense terminals. And this should be 1 milliohm. And that's pretty close. 1.02-ish milliohms. Hope that's visible, is it? 1.02. Okay. This big brute here is 300 amps, 60 millivolts, which means 0.2 of a milliohm. try and get these clips onto him. We should get 0.2 milliohms. Pretty close, 0.2. And very hard to read, but this is 50 millivolts at 250 amps, even with rusty sense terminals. So that's also 0.2 of a milliohm. Yeah, not quite as good. Actually, I did get better readings of this before. Oh, there we go. That's very close to 0.2. There we go. So, even for measuring less than a milliohm, this isn't too bad. I wouldn't trust it without checking the current with something like this first, but for say 10 milliohms and above, you could probably just work straight off the theoretical value of dividing the voltage, the reference voltage 1.25 by the resistance you put here to get the current. And you could probably just, that's probably close enough to get fairly accurate measurements for 10 milliohms or more. So there you go. Isn't that a neat way of getting low current measurements? Hope you found that interesting. Catch you later.